Okay, so let's look at this introduction of ADC. So analog to digital converter, or known as a ADC, are among the most widely used device for data acquisition. Okay, so every time you're going to acquire a data, okay, out there, so you're going to need a ADC device. So digital computer use a binary numbers, which is in the discrete system. But our physical world, everything is in analog, which is we have a continuous signal. So in order to convert from this analog signal or the continuous signal to a discrete signal, you are going to use this ADC. Okay, so a device called a transducer, which is a sensor, is needed to convert physical quantities such as a temperature, you have a pressure, you have a accelerator, and then you have what we call any other physical quantities that you're going to measure to electricals or such as a voltage or current signal. So in order to convert these physical quantities to the electrical signals, you are going to need a sensor. So after you convert them to this voltage or current signal, then after that we are going to fed it to our ADC in order to convert from analog to digital signal. So this is what we call here. It is how we are going to connect our microcontroller to a sensor via ADC. All right, so you have these sensors here. Okay, so before you have a sensor, you have an analog quantities. Okay, your analog signals that you're going to acquire or you're going to convert. All right, and then you have a sensor. So this sensor will capture the analog signals, and it will convert the physical quantities of your analog signal to the electrical signal, okay, such as a voltage or a current. Okay, once the sensor convert it to electrical signal, so what happens is it will go to ADC. Okay, so inside of this ADC, this analog value, all right, will be converted to digital value. All right, so then from this ADC, okay, all the what we call here, all the digital value here will go to the CPU in order to do some processing. Okay, either you're going to subtract, you're going to do addition, you're going to do a logical anything. Okay, you're going to process it inside of your CPU. When you then process that signal, that digital signal, then you're going to display it to your output. Okay, you will send all the processed data here, okay, and display it to your output. Okay, so ADC actually is used to translate the analog signal to digital signal. In Addmarks 32, okay, and N-bit ADC is used to translate the analog signal to digital signal so that microPIC can read and process them. Okay, so some of the major characteristics of ADC that we need to know. Okay, so we have a few characteristics inside of ADC that you need to familiar with. The first one here, we call it as a resolution. Okay, so ADC has N-bit resolution. Okay, according it depending on the chip that you're going to use. Some of the ADCs has 8-bit resolution. Some of them has 10-bit resolution, 12-bit, 16-bit, and some of them got 32, 64-bit, depending on the chip that you're going to use. Okay, for Addmarks 32, okay, the resolution is 10-bit size. Okay, so you have for the Addmarks 32, the resolution is 10-bit. So higher resolution ADCs provide smaller step size, which is a smallest change can be recognized by an ADC. Okay, so higher resolution, good step size. Okay, so the conversion will be better. Okay, although ADC resolution is fixed, but the step size can be controlled by VREF. Okay, so this is the table resolution versus the step size for ADC. Okay, so we take our V reference equal to 5 volt. Okay, so this VREF, okay, it can be either 5 volt or it can be your any V in that you're going to put, or it can be internal voltage. Okay, so for this table 13.1, okay, we just assume that the VREF is 5 volt. Okay, so this is the resolution. Okay, if you have a 8-bit resolution, so the number of steps is 256. All right, so how to calculate the step size? Okay, this step size here, step size equal to VREF, okay, divided by number of your steps. Okay, so means that every small changes equal to 19.53. Okay, for 8 bits. Okay, contoh dia macam ni lah. You have a 8 bits. Okay, which is the 8-bit value is from 0, 0, 0, 0, 0, 0, 0, 0 until 1, 1, 1, 1, 1, 1, 1. Okay, for the 0, it will represent by 0. And then if you have a 0, 0, 0, 0, 0, 0, 0, 1, so this is equal to 19.53. And then if you for the next number is 0, 0, 0, 0, 0, 0, 1, 0. So this is equal to, okay, 90.93, and then you plus with another 90.93. So you will get something like 38, 39. Okay, 39.0. So this is your step size. Means that every increment of this ADC value. Okay, so the step size is 19.53. Okay, if you have a 10-bit, okay, so the number of steps is 1024, and the step size is 5 over 1024, then you will get 4.88 millivolt for each of this increment of this value here. Okay, so this is the resolution. Resolution means that the ADC size, okay, the size of your ADC. Either you're going to use a 8-bit ADC, 10-bit ADC, 12-bit ADC, and 60-bit ADC. So from this ADC, okay, this n bit here, you will get the step size, but you need to know lah what are your VREF. Okay, that is the first characteristic that you're going to know, which is a resolution. And then the second one, we call it as a conversion time. Okay, so this conversion time is time ADC takes to convert from analog input to digital number. So this is the time that you're going to convert from, you have an analog. Okay, you have an analog and then you're going to convert to digital. So what are the time to do the conversion? Okay, so that's one is we call it as a conversion time. And then we have a VREF. Okay, so VREF is your V reference. It's input voltage used for the reference voltage. Okay, so the voltage connected to this pin along with ADC resolution will dictate your step size. Okay, so as we see earlier, okay, step size equal to VREF divided by your resolution, your steps by your resolution. All right, and then number 4, characteristic number 4 is digital data output. Okay, so in an 8-bit ADC, we have an 8-bit digital data output of D0 to D7. So this is the digital data output. Okay, so this is the digital data output. If you have 8 bits, so the first digital data output to represent 0 volt is 000 000 000. Okay. If you're going to represent a 5 volt, it is a 11111111. So that is a D out. Okay, so D out equal to V in. Okay, what are the value that you're going to convert divided by your step size. Okay, so this is the step size. Okay, Vref over your number of step, and then after that, okay, you do this calculation here, then you will get what are your D out. Okay, so that is the digital data output. Okay, and then we have next is a parallel. Okay, so before that, okay, let's look at these examples here. Okay, so for example, you have a 8-bit ADC. Okay, and then the Vref, the reference voltage is 2.56 volt. Okay, so you're going to calculate what are the output if the analog input is 1.7 and 2.1. So you're going to find out what are 1.7 volt, okay, represent in the digital value. Okay, so how to do that? Because the step size is 2.56 divided by 256, so you get 10 millivolt. So this is your step size, and then you know that the D out is sama dengan V in divided by step size. Okay, so this is your V in, okay, which is 1.7. Okay, and then you divide it with 10 millivolt, you will get 170. So this 170 is in decimal value. So in order to get the D out, you need to convert it to binary number. Okay, so by convert it to binary number, you will get D is the number 10101010. Okay, which is will represent the 1.7 volt. Okay, if you're going to convert 2.1 volt, which is this analog value, okay, and then you're going to find out what are the D out, the digital value. So 2.1 divided by your step size, so you have 2.1 volt divided by 10 millivolt, then you get 210, and this 210 you convert it to binary number, so you will get this value. Okay, and then characteristic number 5, okay, which is a parallel versus serial ADC. Okay, so for the parallel ADC, 8 or more pin dedicated to bring out the binary data. Okay, it depending on the resolution. Okay, the resolution that you use. If you have a 8-bit resolution, so you have 8-bit pin out okay, to bring out this value. If you have a 10-bit resolution, then the number of pin out to bring out this value, okay, the binary value will be 10. Okay, so parallel ADC, 8 or more pin dedicated to bring out the binary data at one time. Okay, if you have a serial ADC, means that only one pin for data out. Okay, so this is your input and this is your output. So you have a parallel ADC, you have 8 input, 8 output, and if you contoh lah, if you have a serial ADC, you have 8 input but only 1 output. Kat sini. Okay, so you need to to send 8-bit value here, you need to send one by one lah. First, you send the low significant bit, and then after that, send out this bit here until the most significant bit. So for the 8-bit, you need 8 cycles lah for this serial ADC. Okay, next is analog input channel. Okay, so many data acquisition application need more than one ADC. Okay, you need more than one input channel. So this ADC chip come with either 2, 4, 8, or even 60 channel on a single chip. Okay, depending on Addmega that you're going to use, the number of the input channel will vary from chip to chip. Okay, for Addmega 32, the number of input channel is 8. Okay, and the last but not least is successive approximate ADC, which is widely used to convert analog input to digital input. Okay, so this approximate ADC has 3 main components, which is successive approximate register, SAR, comparator, and control unit. Okay, so that is for the ADC characteristic. Now we are going to see how to write ADC program by using C language. Okay, before we going to do the ADC programming, so let's familiar with the Addmega ADC features. Okay, so this is a Addmega ADC features that you need to know. Okay, the first one here. Okay, this is the important one lah. Okay, Addmega 32 have 10-bit ADC. Okay, kamu ada 10-bit ADC. Okay, so the resolution is 10-bit and it has a 8 analog input channel. Okay, as I mentioned earlier, ada 8 analog input channel, which is from this 8 analog input channel, okay, you can divide it to 7 differential input channel and 2 differential input channel with optional gain of 10 times and 200 times. Okay, later we will see more detail on this differential input channel. Okay, and then the converted output binary data is held by 2 special function register. Okay, so the D out, okay, will be saved to these registers here, called as a ADCL and ADCH. Why we need to have 2 registers? Kenapa kita kena ada 2 registers kat sini? Is it 1 register not enough? Why? Kenapa? Can somebody tell me why we need to have 2 registers? Okay, to send out the output binary. Okay, to send out our D out. Kenapa? Okay, because this year, okay, ADC for Addmega 32 is 10-bit. Okay, our register for Addmega 32 is only 8-bit. Okay, so to make it as a 10-bit, you need to have 2 register. Okay, to save to store this 10-bit ADC value. Okay, so since ADCH and ADCL give us 16-bit, okay, and our ADC data out only 10-bit, okay, so those you have 6-bit are not used. Okay, so remaining 6-bit is not used. Okay, since okay, this is our ADCH, and then we have okay, so this is your ADCH, and this is our ADCL. Okay, so you have a 16-bit, but your ADC only 10 bits. Okay, so this is 8-bit. So and then we add with 2. Okay, and then this remaining 6-bit is unused. Okay, tak digunakan. Okay. So there are 3 options for VREF. Okay, for Addmega 32, we have 3 options for VREF. Okay, one is connected to VCC. Okay, which is we take it as a 5 volt. And then we have an internal 2.6 volt and external ARF pin. Okay, so your VREF have 3 options: 5 volt, 2.6, and external ARF pin. And then the conversion time detected by crystal frequency connected to your STEL and it will be controlled by this bit here. Okay, you can determine your conversion time according to setting that you will done in this bit. Okay, we call it as a ADPS 0 until ADPS 2. Okay, later we will see more detail on this, how to do the conversion time setting. Okay, so again, okay, so this is your Omega 32 pin out, right? So this Omega 32 pin out, okay, to do the ADC conversion, okay, you need to make sure that all the sensor must connected to your port A. Kenapa port A? Because your port A have a special function called ADC. Yes, it has a special function, okay, which is ADC. Okay, if you put a sensor dekat sini, port B, port D, or port C, so it will not convert your analog signal to digital signal. Only sensor that connected to your port A can do ADC conversion. Okay, and then next slide is how to do the ADC connection and programming. Okay, so we use inductor and capacitor in order to get a stable voltage source to the AVCC pin. Okay, so every time you're going to do a ADC, okay, so make sure that, okay, you have this inductor and capacitor connected to your AVREF, ground, and AVCC dekat pin 30, 31, and 32. Okay, so this is the recommended connection lah, okay, for the ADC. If you're not going to do any conversion, ADC conversion, so no need to put this circuit here. Okay, if you're going to use the ADC, okay, to convert from analog to digital, then you need to have this circuit, okay, in order to get a stable voltage source. Okay, and then in Omega 32, there are 5 major registers are associated with ADC. Okay, this is the 5 registers that you need to know. Okay, and the first one here, we call it as a ADCH and ADCL. So this is where you store your result after conversion. Okay, so this is where you put your D out. Okay, so your D out will be stored inside of this register. Then we have the ADC SRA. So this is an ADC control and status register. Okay, so this is where you're going to put your setting. Okay, all the setting will be done inside of this ADC SRA. And then we have an Addmarks. Okay, so this Addmarks used for ADC multiplexer selection register. Okay, so later we will see what we are going to do for the Addmarks. And last but not least is SPIRE. Okay, special function IO register. But for this course, we only focus on this 4 register. Okay, the SPIRE we will exclude from our syllabus. Okay, so first let's look at the Addmarks register and what this Addmarks do. Okay, so there are 3 options for VREF selection. Okay, one is coming from AREF pin. The second one is coming from AVCC pin. And the third one is coming from internal, which is 2.56 volt. Okay, so usually this AVCC pin, the VREF is 5 volt. Okay, so by using this, what we call here, Addmarks, okay, you will determine what are the VREF that you are going to use. Okay, kat mana kita nak do this setting? Here, ref at bit 7 and bit 6. Okay, so this bit 7 and bit 6 used to select your reference voltage. If you put 0, 0, okay, you put 0, 0 at bit 6 and bit 7. So your AREF okay, your VREF coming from AREF pin. Okay, if you put 01, then your VREF is coming from AVCC, which is 5 volt. Okay, so this one, kalau kamu choose 00, it depending on your RF pin lah. If you put your RF pin with 10 volt, then the VREF will be 10 volt. If you connect your RF pin with 20 volt, so then your VREF become 20 volt. Okay, if you choose 01, means that you're going to make your VREF same as your VCC, which is always 5 volt. Okay, and if you put 10, okay, this one is cannot lah, because this is for reserve. Okay, you cannot put 10 here dekat sini. And if you put a 11, okay, at bit 7 and bit 6, then you're going to use the 2.56 volt, which is your internal voltage. Okay, so this is how you're going to select your reference voltage, which is you can do it by do a setting inside of your Addmarks register. Okay, and then you have this ADLA here. Okay, so what this ADLA do? Okay, this ADLA, okay, use, okay, to determine either your ADC is left adjust or right adjust. Okay, since our ADC is 10 bit and ADCH is 16 bit, okay, you have ADCH 8 bit and ADCL another 8 bit, so total number of bit here is 16 bit. So by do a setting dekat ADLA, so you're going to determine lah either it is right justified. Okay, this is a right justified lah. Okay. Okay, so this is the right justified or left justified, means that you use all the 8 bit at the left and then another 2 bit from your low ADC and the remaining of 6 bit unused. Okay, so we'll do a setting inside this ADLA. And then the max 4, okay, which is this bit 5 until bit 0 here. Okay, sorry, bit 4 until bit 0 is used to determine the analog channel and gain selection bits. Okay, so you're going to determine which channel that you're going to use. Is it ADC 0, ADC 1, ADC 2, or ADC 7? Depending on the sensor that you're going to put. If you put your sensor to this ADC 7, so make sure that the setting dekat sini is correct lah. Okay. So this is the what we call here the explanation for the max 4 to max 0, which is from bit 4 to bit 0 in Addmarks will determine the analog channel and gain selection to be used. Okay, there are 2 types here of analog channel. Either you're going to use a single-ended or differential input. Okay, let's look at the single-ended first. Okay, so if single-ended is selected, you can choose input channel among ADC 0 to ADC 7, which is single pin is used as an analog line and ground as a common ground. Okay, it's something like this lah. Okay, you have what we call sensors here. Okay, usually your sensor have the positive and negative terminal. Okay, so your positive terminal you will connect it to your ADC channel, while negative you connect it to your ground. Okay, so this is where you're going to. This is what we call it as a single-ended channel. Okay, so if you connect your sensor to channel 0, ADC channel 0, so the setting that you're going to put to your, this marks here is 000000. Okay, let's you put your sensors or to ADC 5. Okay, so this sensor here, you need to set it to this Addmarks Register 00101. Okay, so make sure that the sensor and this value here is correct lah. If not, okay, the CPU will not will unable to get the signal from your sensor. Okay, if differential input is selected, okay, if you're going to use a differential input, okay, you can choose input channel as well as the op-amp gain, either, okay, no gain with a 10 gain and 200 gain. Okay, so this is where you're going to put. Okay, contoh lah. Okay, so you're going to use a 10 times gain. Okay, so make sure if you're going to use a differential input, okay, with a 10 times gain, so make sure that your sensor, okay, your positive differential input go to ADC 0 and another one go to this one, right? So this is how you're going to what we call here to do the connection. Okay, so that is for how we're going to put our sensors, and usually, okay, usually we focus on this single-ended lah. Okay, not the differential input unless you're going to use gain. Okay, if you're going to use gain, then you need to do the differential input. Okay, then we have the ADLA, as I mentioned earlier. Okay, ADLA, which is at bit 5 in Addmarks, will determine either the left bit or the right bit of your ADCH, ADCL register used to store the result, which is you're going to put your result either it is a left justified ataupun right justified. Okay, so since AVR is 10 bit and we have a 2 registers here, which is a combination of these 2 registers, total is 16 bit. Those you have 6 bit are not used. Okay, so now you're going to what we call here to determine. You need to determine lah. Either you going to make it as a left justified or right justified. Okay, by default, okay, we use the right justified because we put 0 to. Okay, if you put 0 to your Addmarks, okay, the contoh lah. This is your Addmarks. Okay, if you put this bit 5, okay, you put 0 here means this is right justified. Okay, you will use the 8 bit from your ADCL and then remaining of 2 bit from ADCH. Okay, so this is a right justified. Okay, by default, we use right justified. If you're going to use a left justified, okay, this is a default. Okay, by default, we make it as a right justified. Okay, if you're going to make it as a left justified, then you need to put 1 to bit number 5. So what happened here is, okay, all the bit here, okay, you see this is your bit 0 and this is your bit 9. So this is your MSB and this is your LSB. Okay, for the left justified, this is your MSB and this is your LSB. You see here all the 8 bit inside of ADCH is used, and then remaining 2 bit from the ADCL is used. Okay, other than that, you not use that. Okay, and then we have the ADCH and ADCL register. So this register used to store the result after the analog to digital conversion is complete, which is you're going to store your D out. Okay, so all of the D out will be placed to your ADCH and ADCL. Okay, again, since the ADC is 10 bit, okay, you're going to need to have 2 ADC, which is ADCH and ADCL. All right, and then make sure that, okay, inside of your ADLA, okay, Either you're going to make it as a right justified or left justified. Okay, by default, we make it as a right justified. Okay, that is for the Addmarks. Okay, so as what we call here, as a conclusion for the Addmark. Okay, so this Addmarks here used to select your VREF. Either you're going to use a AREF as a VREF ataupun VCC or 2.5 volt. And then number 2, okay, either you're going to make it as a left justified or right justified. Okay, this one here you can set it at the Addmark. Okay, which is bit number 5 inside your Addmarks. Okay, and then 3 is you're going to select, okay, to select ADC input channel. Okay, so make sure that the ADC input channel that you use is correct according to your circuit. Okay, that is for the Addmarks. Okay, next we are going to see for ADC SR Register. So the ADC SR Register is the status and control register of ADC. Okay, so ADC SR is a 8-bit register. Okay, so this is the what we call here the things that you need to familiar. Okay, for this ADC SR register. Okay, first is addend. Okay, bit nombor 7 ni, this is for addend. Okay, so this is ADC enable. Okay, so this bit here will enable or disable the ADC. Okay, so setting this bit to 1 will enable the ADC. Means that every time you're going to make a ADC conversion, make sure that the addend is set to 1. Okay, so this is very important lah. Okay, to do a conversion, make sure that addend is set to 1. If not, all the ADC is disabled, so you cannot do the ADC conversion. Okay, and then the next bit that you're going to set is at this ADC, okay, which is bit number 6. Okay, this one also another important bit. Okay, so this bit number 6 used to start your conversion. Okay, so to start your conversion, you need to put 1 here. If you put 0, then what happens is, okay, the conversion will not started. Even though you put addend equal to 1, ADC is 0, then the conversion will not start. Okay, so to start the conversion, you need to make sure that ADC you put 1 as well as your addend you put 1 as well. Okay, and then we have a bit number 5. Okay, this is edit. Okay, so this is a ADC auto trigger enable. So auto triggering for ADC is enabled when you set this bit to 1. Okay, so this one here, okay, we can skip this bit. Okay, so the next bit that you need to know important bit is bit number 4, which is this is a ADC interrupt flag. Okay, so this bit is set when your ADC conversion completes and the data register are updated. Okay, means that this ADIF will be set after you already convert from analog to digital, and then that value, that the out value already placed, okay, already put to your ADCH and then ADCL. Okay, once done, and then your ADIF bit here kat sini, okay, your bit, this bit 4 here will be set, automatically set 1. If the ADIF is 0, so the CPU know that the conversion not yet finished. Okay, once the ADIF equal to 1, then the CPU know that, okay, we already finished conversion. Okay, so this is important lah. Okay, kat sini important. And then bit number 3 also another important bit, which is this ADIE, okay, stand for ADC interrupt enable. Okay, so if you're going to make an ADC interrupt, so make sure you enable this bit here. Okay, so setting this bit to enable the ADC conversion complete interrupt. And last but not least, okay, these 3 bit here also another important bits. Okay, which is this bit here will determine, okay, your conversion time. Okay, so this bit determine the division factor between your external frequency and the input clock to your ADC. This one here macam your prescaler. Okay, similar to your prescale in timer. Okay, which is you're going to decide what are the best conversion time that you're going to use. Okay, so from this ADC SR on, okay, we can ignore this edit here, bit number 5. Other than that, you need to make sure you need to know, okay, and set them correctly. Okay, Josh asking that can explain again what RD is for. So this RD, mana tadi RD? Okay, this RD. Alright, this RD here, if you're going to, okay, for ADC, actually ADC, we have 2 types of ADC. One by using a polling method. Okay, the second one we use a interrupt method. Okay, if you're going to use an interrupt method, so you need to make this RD equal to 1. Okay, if you're going to use a polling method, okay, so no need to put the no need to set this bit 3 equal to 1. Okay, so depending what method that you're going to use in order to do ADC conversion. Okay, you already learned about the polling method and interrupt method in the previous module. Okay, what are the difference between polling and interrupt? Okay, so let's look at the last 3 bit of the ADC SRA, okay, which is this one here used for the ADC Prescaler of conversion time. Okay, so this bit will determine the division factor between your external frequency and the input clock of your ADC. Okay, if you put 0000, okay, dekat, okay, if you put 000 at this bit here, so what happened? Okay, so this one cannot use lah because this is a reserve. If you put 001 means that you are going to divide it, you use a prescale 2, which is you need to divide it your external by 2. 010, which is you use a prescale 4, and then 0118 followed by 16, 32, 64, and 128. Okay, so in order to select your conversion time, you can select any of these prescale here. Okay, so this FOSC, okay, or prescaler is the split of the crystal frequency that are connected to your AVR. Okay, and then this is the most important part here. For the AVR, ADC requires an input clock frequency less than 200 kilohertz for the maximum accuracy. Okay, so make sure that your, what we call here, your frequency, your clock frequency is less than 200 kilohertz. So that's why you need to determine which prescale that you are going to use in order to make sure the clock frequency is less than 200 kilohertz. Okay, why? Because if you use the clock frequency greater than 200 kilohertz, what happens here? The accuracy for the ADC conversion will become lower. Okay, to have a maximum accuracy, so make sure that the clock frequency is less than 200 kilohertz. Okay, for example, let's look at this example here. Okay, an AVR is connected to 8 megahertz crystal oscillator. Okay, so you connected your ADC to 8 megahertz. Okay, you have a extra 8 megahertz. And then you're going to calculate the ADC frequency for ADPS2, which is 001. Okay, so this is the setting. A is at 001. B is the 100. Okay, you put your ADPS2 to 0100, and C is 111. Okay, for this one here, you know this is divided. You use a prescale of 2. What about 100? Okay, so 100 is 16, and 111 is 128. Okay, so it is a 16, and it is a 128 prescale. Okay, so now what you're going to do, you need to find out your new clocks. Okay, your new frequency. So F new equal to F divided with your prescale. Okay, so 8 megahertz divided with 2, you get 4 megahertz. Okay, can you use this clock frequency? Can you use this frequency? Cannot. Why? Because our target here, the frequency must lower than 200 kilohertz, so that we have a maximum accuracy. So we cannot use this. Okay, because the frequency here is 4 megahertz. So cannot use this setting. Okay, and then we take a 16. So what happened? F 8 megahertz. You divide by 16, then you get 0.5 megahertz. Okay, which is equal to 500 kilohertz. Can you use this frequency? Cannot. Why cannot? Because this frequency is greater than 200. So this one also cannot. Okay, so you need to find out. Okay, so you need to determine what are the prescaler that what we call here, the best prescaler that we need to use in order to make sure our frequency is less than 200 kilohertz. Okay, let's choose 1 to 8. Okay, so 1 to 8, so you have 8 megahertz divided by 1 to 8. Okay, you will get 62 kilohertz. Can you use this frequency prescale? Yes, you can use this prescale. Why? Because this 62 kilohertz is lower than the target frequency. So you can use this one. Okay, let's Okay, instead of use the 1 to 8 prescaler, okay, we have another prescaler kat sini, 64. Can we use the 64? We're going to find out the optimum prescaler, the best prescaler that we can use. Of course 1 to 8 you can use. Okay, let's say we're going to use the 64 prescaler. Okay, 8 megahertz. You divide it by 64. Okay, can you press the calculator? Berapa kamu dapat? Okay, 0.125 megahertz, which is equivalent to 125 kilohertz. Can you use this one? Boleh tak? Okay, can. You can use this prescaler as well. Okay, and then kita cuba lagi another prescaler here. Okay, which is 32. Okay, so 8 megahertz divided by 32, so you will get 0.25 megahertz, which is equal to 250 kilohertz. Okay, so this one cannot. You cannot use this one. Okay, so based on this answer here, okay, 64 and 128. Okay, contohlah, the question asks you, okay, use the optimum prescaler. Okay, which one that you're going to use? Is it 64 or 1 to 8? Which one you're going to select for the optimum prescaler? Mana satu yang kamu nak pakai? Is it 64 or 1 to 8? Because from this calculation here, you know that, okay, both is lower than 200 kilohertz. So which one you're going to choose that use the optimum prescaler? Okay, so you need to choose 64 lah, because this is the optimum prescaler. Okay, so I think we stop here. Okay, next week we will continue with how to, okay, the step that you're going to use in order to write the ADC programming. Okay, so first we're going to see for the polling, okay, by using a polling method, and then after that we're going to see the step by using the interrupt method. Any question? Ada soalan tak sampai sini?